we are still talking about the convergence divergence. So we're good here. Let me see. I don't even know what to do the heading with anymore. I'm just going to go and say Calc 2. I know it's IPX. The lectures are a little bit off, slash IPX. Calc, there you go. And it's the same, whatever lecture you're on, it's two different ones. Calcture? Mathy magic. All right, so we last left off about investigating convergence of infinite series. And we discussed three different tests so far. One was the nth term test. Screens look good for divergence. We talked about the geometric series test. And we talked about the telescoping series test. Now, both these last two tests are based on the process that if we can calculate what the sum is, then we know that there is a sum. Now, with the geometric series test, though, you're not meant to actually find the sum of the series unless I requested you. So if I specifically say find the sum of the converging test, or I might say something like on your final, determine if the series converges and find the sum if it converges. So basically, in that scenario, you know that I'm either talking about a telescoping or a geometric series test specifically. I could also say something like if it is geometric or telescoping, find the actual sum. But again, you're just checking if it converges, not what it converges to. All right, now we're going to talk about a new one, 4. And that's the p-series test. Now, the p-series test is any series that is written as the sum of 1 over n to the p. And typically we go from, we can say from n equals I to infinity. And if we wanted to, we can say a constant times this one right here. Now, again, I had mentioned this kind of like in our last lecture that there's a lot of confusions about what other series look like a p-series test, when there's multiple terms in the denominator. But when there's multiple terms in the denominator, that does not mean that it actually converges. That it's not a p-series. It has to have just one term on the bottom, n to a power. And the reason is because of the proof that we're going to be doing right now. And in going over this series, 1 over n to the p, we're going to talk about the scenario that what happens if p is greater than 1. So if p is greater than 1, then the visual of what we are looking at is going to look like this right here. And this is the graph y equals 1 over x to the p, which we can define as our function f of x. And when talking about p being greater than 1, any value greater than 1, since p is greater than 1, a sub n will always be positive, and a sub n plus 1 will always be less than a sub n, which is just a fancy way of saying what? Decreasing. The other thing that must also be true, finally, is that the limit as n approaches infinity of a sub n will also equal 0. Now, why am I noting this? Because as I mentioned in the last class, there's certain conditions for the other tests that you must double check. And for this test, basically by calling it a p-series and saying p is greater than 1, then all of this information is automatically assumed that you have stated that. So when you say this is a p-series, you technically could say that, that's a positive function and it's decreasing and you kick the tire and the door stayed on. All that kind of stuff is an assumption based on that fact that you're calling it a p-series. So that's why saying something is a p-series is very specific. Whereas those other ones, when it's not a p-series, it can go up and back down, and it's not necessarily always decreasing. Okay? So why is this important? Why is this graph important? Because we can look at the values 1, 2, 3, 4, and so forth. And when we break this up as such, this would be right here, f of 1. This right here would be f of 2. I know, sorry, it's a little squished. This would be f of 3, and so forth in regards to matching the value that is right here. Yes?
Are we assuming x is greater than 0?
Yes, because it's n is equal to I, so I guess we would say that I is greater than 0. So yes. So typically on this one right here, we're looking at, in this piece, the summation from I equals, well, in actual limit, I'm gonna show that as a part of the proof. Okay, so we've done Riemann sums, and we can actually, if you think about this right here, the area of that piece is equal to what? F of 1. It's f of 1 times 1. This area right in here would be f of 2. This area, f of 3. This area, f of 4, and so forth. If I am using a right Riemann sum. All right? So what's happening here is I'm using a right rectangular approximation. All right, so when I use a right rectangular approximation, that's the visual I get. All right, so let's say now that we want to calculate the sum from n equals 1 to infinity of 1 over n to the p. Well, if I want to find the sum of 1 over n to the p, that's going to be the same thing as f of 1, right? Because f of 1 is plugging in n equals 1, which would be 1 to the p, plus f of 2 plus f of 3 plus ... which again is the same thing as 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, ... And this would therefore be equal to, well, what's 1 to the p? 1. So this is equal to 1 plus the series from n equals 2 to infinity of 1 over n to the p. And you'll see why I'm writing this and breaking up. So let's say we wanted to find the series from n equals 1 to infinity. That's going to be the same thing as the first term plus the series from n, the next term, 2 to infinity. So if we were doing from 2 to infinity, we could break it up as like 1 over 2 to the p, which is a known value, plus the series from 3 to infinity. Okay? So basically, what's important here is that what we can say is that if this series converges, then 1 plus the series converges. Right? If you have something that converges and you add a constant, you still get something that's convergent. All right? Well, if we look at this visual here, we can actually think about this right in here. What is this green part that I have just highlighted? The integral, also known as a improper integral, right? And so the series, why am I just, my series from n equals 2 to infinity of 1 over n to the p, it's also a little bit strange for me to stand up during the lecture, I haven't done that in quite a while, is going to be less than or greater than the improper integral. It's less than, because again, when using a right Riemann sum and you have a decreasing function, you know that the right Riemann sum will be less than the actual area. That's what we learn in typical Calc AB. And so that's what we did. It's less than the actual area, which is the integral from 1 to infinity of 1 over x to the p dx. And therefore, if the improper integral converges, then the series must converge.
What's the purpose of that first step then? Could you not just do it from 0 to infinity?
Since less than the integral. I'm going to get you I'll get you that on the next part. So you're going to see the cool thing with that 1 plus is going to happen in the next piece when I prove divergence. So it'll get there. So we need to check to see if this improper integral converges. So we now need to prove that the improper integral always converges when p is greater than 1. So the integral from 1 to infinity of 1 over x to the p dx when p is greater than 1 is equal to the limit as b approaches infinity of the integral 1 to b of x to the negative p dx, which is equal to the limit as b approaches infinity of 1 over negative p plus 1 times x to the negative p plus 1, evaluated from 1 to b, using our work from just doing improper integrals. Following along? Which is equal to the limit as b approaches infinity of, this is just a fancy way of saying 1 over 1 minus p, negative p plus 1, right? And then when I flip it down, it's going to be 1 minus p on the denominator. So I'm going to get times 1 over b to the p minus 1 minus 1 over 1 to the p minus 1. That's a p minus 1 right there. Okay? Which, remember, if p is greater than 1 on that part right there, what does this piece go to when p is greater than 1? It's going to go to 0. As long as p is greater than 1, that term is going to go to 0, which is going to leave me with the answer of 1 over 1 minus p times negative 1, which is 1 over p minus 1, which is what it converges to. The series. So what we've proven is, therefore, when p is greater than 1, then the series from n equals 1 to infinity of 1 over n to the p must be less than 1 plus 1 over 1 minus p. Now, the mistake that a lot of students get is that we believe we have found what the series converges to. we have not found what the series converges to, just that we know that it is less than this value right here. We're technically going to be finding some boundaries when we find a divergence piece as well. You can kind of prove that it's going to be more than this, but less than this type of thing. But we do not know what the actual series converges to. We just know that it must converge. There's a difference there. Okay? So we just know that it's less, not that that's what it converges. So therefore, what we say is that the series from n equals 1 to infinity of 1 over n to the p, it is a p series. We can just identify as a p series where p is greater than 1. Therefore, it converges by the p series test. Now, we don't actually have to do the whole integral and proof like that, because what we've done here is that we've proved that for no matter what the value of p is, that as long as it's greater than 1, then we know that this statement was automatically be true. So if it was 1 over n to the 1.1, okay, that's going to converge to this value, or at least less than this value right here. It just doesn't tell us what it converges to, but we know it will. Questions? Okay. Yeah.
When we do like problems with this,
Mm-hmm.
do we have to say like converges by like the test?
Yes. You have to identify which test it is and if there's any conditions. So in this case, basically the conditions are you state that it's a p-series and you state the p is greater than 1. And then you can conclude that it converges or diverges by that test. Good? All right, so what happens if p equals 1? Well, in the scenario where p equals 1, then we have this series from n equals 1 to infinity of 1 over n. All right? Which visually was once again this function right over here, which is going to be the function f of x equals 1 over x, right? And similarly, if we go from 1 to 2 to 3, we can use a left Riemann sum in this scenario, where this area here is going to be what? That's f of 1. This area here is f of 2. This area here is f of 3. And of course, we would continue that process over and over and over. So if we use a left Riemann sum, all right, if we use a left Riemann sum, then the series from n equals 1 to infinity of 1 over n must be what? Mm-mm. It must be greater than, because it's going to be greater than the the integral from 1 to infinity of 1 over x dx. And so this is where that question that came on earlier, like what? So it's a really cool trick in my opinion. When we do the 1 plus, then we know that we will get less than. So basically what it's doing for us, it's kind of giving us a boundary of what the two convergence pieces are going to be. So you can actually think about it if you want to, you know that the sum would be greater than the integral from 1 to p, but less than the 1 plus the integral from 1 to infinity. So you know that it's going to be between those boundaries. But basically what we're saying right here is that, okay, if I use a left Riemann sum, then each of the rectangular areas would be greater than the actual areas, which is the summation. So my summation is actually greater than the improper integral. So therefore, if the improper interval diverges, and the sum is greater than the improper integral, then we must also diverge. So this is equal to the limit as b approaches infinity of the integral 1 to b of 1 over x dx, which is equal to the limit as b approaches infinity of the natural log absolute value of x evaluated from 1 to b, which is the limit as b approaches infinity of the natural log absolute value, b, which is just 1, minus the natural log of 1, which is just 0. But this term is now going to go to infinity, and therefore it diverges. Therefore, if our series is greater than something that diverges, then our series must also diverge. And so therefore, the series from n equals 1 to the infinity of 1 over n to the p, when p equals 1, this is a p series.
You can also just add the harmonic series divergence.
Yeah, I'm not a fan of that. P equals 1, therefore it diverges by p series test. But yes, that is one from physics if you're using that idea right there. But you can just identify it's just p greater, and as we're going to see, it's p less than or equal. If as long as p is greater than 1, it converges by the p series test. Less than or equal to 1 diverges. So I just got to prove real quick, and I'm going to do a really quick one. I'm not going to get too much into it. Literally, I'm going to use this amount of space right here. All right. If 0 is less than p is less than 1, we just get the same scenario as p equals 1. And therefore, it would also diverge. All right, with all that said, now we can actually define the p-series test now that we see the proof as to why. There's always that confusion. So why is that happening? This p-series is a specific series that is always decreasing from 1 to infinity. And that's why it's specific and it doesn't have any terms. It's 1 over n to the p. And it technically does not matter if we start at 1 or 2 or 3, because if you start at 3 to infinity, well, if the series from 1 to infinity converges, then 3 to infinity converges. It's a constant plus something that's going to converge. And the same thing, if something diverges and you start at 3, well, it's going to be some constants, f of 1, f of 2, f of 3, plus something that diverges, which diverges. So the p-series test, again, basically now says that if it's a p-series, where p is greater than 1, then the series converges by p-series test. Or if p is less than or equal to 1, then the series diverges by p-series test. And that's the entire thing. All right. So the main thing about the p-series test is basically it's the next test that we're doing, but we don't have to prove the integral. Does that make sense? The biggest thing here with the p-series test is you don't have to prove that the improper integral converges or diverges, because it's always true when p is greater than 1, or always true less than or equal to 1 for divergence. And that's what makes it different than number 5, the integral test. Now, the integral test is basically what we just did, but what? Hello, baby. It's my mother. First time she'll have ever seen me teach today. So the integral series is when not a p-series, when not a p-series, but you can evaluate the improper integral convergence / divergence. So we don't, in a p-series, we don't actually have to calculate the improper integral. We don't have to determine if the improper integral converges or diverges, because as long as we say that it's a p-series and we state how the p-series value is, then we know by proof, any scenario for any value of p, we know if it's going to converge or diverge. But if we don't, then we're going to do it right here. Now, something that is important here is that you do have to list the conditions. All right? We do have to list the conditions. What is our first condition that must be always true? Well, the limit as n approaches infinity of a sub n is 0. We kick the tire and the door stays on. The terms must be decreasing, but before we get there, terms must be positive, so a sub n must always be greater than 0. And there must be a decreasing function, so a sub n plus 1 must be less than a sub n for n greater than or equal to I. And this is a little tricky one in a scenario, and when I say n greater than or equal to I, what it means is the function might start by increasing and then become decreasing. All right, so the values of the denominator, like if you think like of a quadratic, right, it might first start to get smaller and then bigger, or bigger than then smaller. And so as long as you can see that, after n equals 3, then it starts to decrease for all terms. But it might not be decreasing for n from n equals 1 to 3. Okay, and that's fine, because if you take something that converges and you add a constant, converges. If you have something that diverges and you add a constant, then it diverges. And all the integral test says is that if, after you stated these facts, if the integral, and if you're starting at 1, if whatever the improper integral is, so, or I, from 1 to the infinity of a sub n dot d sub n, and of course you can just change it to a function of x dx, which is most common. If it converges, and it's basically would be the same proof. You'd add 1 plus and so forth. Converges, then the series from n equals 1 to infinity of a sub n converges. And if the improper integral from 1 to the infinity of a sub n d sub n diverges, then the series from n equals 1 to infinity of a sub n diverges by the integral test. So you actually have to do out the improper integral. So you do have to do all the work and do it properly with plugging in b, with not just plugging in infinity or the convergence values. Now, oftentimes we're just going to see a series that's going from 1 to infinity. And if you see like, well, why does this one go? It could be a typo on my part, but if the bottom was like 1 over n minus 1, then I have to start it at 2. So that's why you might see it do the series from 2 to infinity or 3 to infinity, because you got to make sure that the bottom doesn't have like a blow up term. So with the integral test, you actually have to do out the improper integral. All right? Oh, yeah.
So to prove that the function is decreasing, do you want to see what the derivative and all
You can just state it. Yeah. I mean, if you're really not confused or sure that it is decreasing function, then you might need to check the derivative, and that the derivative is always going to be negative. That's the proper way to kind of do it. You can also, you can just state it. Yeah, you don't have to prove on the integral test that it is, but if it's not always decreasing and it doesn't start decreasing until n equals 3, which I could throw at you on the assessment, then yeah, I would knock off like a point or two. But it's probably nothing to go overly worried about, I would say. It'll be pretty obvious that it's going to be decreasing. All right, let's get into our next one. Sorry, I just got to re-download the notes real quick. Where are we? There we are. All right, number 6. The next one that we're talking about is 6, which is the comparison test. So 6 and 7 are called the comparison test. All right. So just because I need to note this and I'd rather not note it twice. So these comparison tests require that you first prove convergence / divergence of the compared series using test 1 through 5 for the series, the summation of B sub n. And that's where, again, this is where a very common thing comes around and people just overlook it. You forget, you go, well, that's a piece, you have a P series and say, oh, so this diverges because that diverges. But you have to show, like it was a brand new problem, why that series diverges or converges. And most oftentimes, you're going to compare to a series like a P series. So you're going to be like, oh, this series that is a P series converges or diverges because P is greater than 1 or less than or equal to 1. And then you go into the comparison portion of it. And that's just what the most common overlooked thing in this one is. So, and then you're using nth series test. Well, I guess you really don't have to use nth series because you can probably prove that it's an nth term test anyways. So your geometric, you compare to something that is geometric, or because it might be, it looks geometric, but then it has like an extra term on the bottom or 2. It might look like a P series, but it has an extra term or 2 on the bottom. Or it could be something that, that you can integrate, and therefore you can kind of show that your values are always less than the other values. Okay? So the process here is that given the series A sub n, you're going to compare directly to the series B sub n. And this is called the direct comparison test. And here's the truth about the direct comparison test is that you're probably not going to pick it. You're probably going to use its brother or sister, however you want, the limit comparison test. Unless it's really obvious, most of the times, unless I specifically tell you, or you can really quickly see that it's a direct comparison test is going to be easier, it might just make more sense for you to do the next one, which is the limit comparison test. Because this kind of goes to the same question that was just brought up. How do you need to prove that the series was always, or the terms were always decreasing. So then you technically have to prove that every term is directly less than or directly greater than its compared series. So 1, this is the direct comparison test. This is number 6. 1, if a sub n is less than b sub n for every value of n, for n greater than or equal to I, and the series b sub n converges, which again, you must show why it converges, then the series a sub n what? Converges. Basically, you're saying term, for n equals 1, for n equals 2, for n equals 3, are starting at 4, 5, 6. If every single term from a1 to an is less than b1 through bn, then I'm always less than something that diverges or converges, therefore I must converge. Kind of like the sandwich, sandwich test that we had earlier on when doing the basic trig limit. Or 2, if a sub n is greater than b sub n term for n greater than or equal to I, and the series b sub n diverges, then the series a sub n diverges. And I'll just put a little disclaimer here, else inconclusive. So you have to be less than something that converges, or you have to be greater than something that diverges. If you are, now it doesn't mean that the test will converge or diverge for the other scenarios. You could be greater than something that converges, and you could either converge you can either converge or diverge. So you don't know what that answer is. And so that's what oftentimes has the problem. So like if you have like 1 over n squared plus 1, right? So do I have time? Yes, I do have time. So in my example here, let's do a quick example, and then I'm going to do the limit comparison, and we'll take a break. If we have the series from n equals 1 to infinity of 1 over n squared plus 1, all right? Again, this is not a p-series, okay? Then we know that 1 over n squared plus 1 is always less than 1 over n squared. And most of you, when we do a lot of practice, you'll know that this converges. You'll be like, oh, that's like a p-series, and the p-series converges. Then you know what your answer is going to be. But then you'll mistakenly do and say that it converges because it's a p-series. I know, because that's what I did all the time when I was in your shoes. It's not a p-series, but it's less than a p-series that converges. And so I must now show that the series, and this is true for n greater than or equal to 1, right, for all values. The series from n equals 1 to infinity of 1 over n squared is a p-series, where p is greater than 1, so converges by p-series test. I must show that piece in there. So don't forget that. That's the biggest takeaway that I want to say with the comparison test. Therefore, the series from n equals 1 to infinity of 1 over n squared plus 1 converges by the direct comparison test. Okay? Yes?
You have to write like the function that you use when converges by direct comparison test to 1 over n squared.
So you have to prove that 1 over, so that's what I've done right here. So basically this right here is the part of the direct comparison test. So I've proven that 1 over n squared converges, and therefore I've stated the facts that mine is always less than the term for n greater than or equal to 1. So now I can say that my series converges by the direct comparison test. Okay? Yes?
For this one, you can just say that it's less than also.
So he gave me the heads up. He had good deals with something. Gave him a hard time. Take it out on their P set. Due today by midnight. Remember, 11:59 for everybody. So And again, this is kind of like what I was saying earlier. It should be obvious that it's going to be less than, and you don't want to do the direct comparison test if it's not obvious, where it's not like plus 1 on the bottom. Because if I gave you the scenario of 1 over n squared minus 1, the direct comparison is not going to work. But if I do also some like n squared, 1 over n squared plus 2n minus 5 or something like that, where it's less than it for initial values because that minus 5 is actually making that denominator smaller for like n equals 1, right? And I guess you could say there's some issues or not. But then eventually the plus 2n is going to overtake that minus 5 or whatever that was there. And so eventually it will. So you could prove it, but in my opinion, it's just not worth doing a direct comparison test unless it's very obvious, like plus 1 plus n plus n+1. So if you see a minus on the bottom, just stay away from the direct comparison test.
So if it's obvious, we can just say it's less than.
Yes. This leads us to the other one, number 7, the limit comparison test, and then we'll take our break. So the limit comparison test is basically like growth rates that we learned earlier. If a sub n and b sub n have the same growth rate, then both a sub n, the sum a sub n and the sum, the series b sub n, they both converge or both diverge. And we can show that by taking the limit as n approaches infinity of a sub n over b sub n, and as long as this is a constant, a non-zero constant, so just to note, C cannot equal 0. As long as this is a constant, then they must have the same growth rate. They grow at the same rate, just like how we learned when we were talking about the limit as n goes to infinity for the other terms. Oh, they have the same growth rate, so I take the leading coefficients. So they both will diverge or converge. But again, you must prove that why that is occurring.
Is there ever a point where the limit comparison test is it like this direct comparison test, or should we always just
The previous example. It was like 1 over n squared plus 1. Like the bottom is always 1 bigger than the denominator is always 1 more than 1 over n squared.
what if I did do it with the limit comparison?
Yeah. Unless I gave you a problem that says show one with, like on the P set, what I had for you on the P set, but we had to truncate it, was you had to have used every test at least once. So in that scenario, you're kind of forced, your hand is forced to find one that you can use a direct comparison test. So I could theoretically, which I'm not going to, ask you to specifically use the direct comparison test. And the reality is the options. I'm gonna release a flow chart graph type of thing, is like if this, and how you should kind of go about doing it at the end of this lecture. So let's look at this example before we go to break. We want to look at the series from n equals 1 to infinity of 2n plus 5 over n squared plus 5n plus 17. Now, when looking at this, you're like, whoa, I don't know what to do here. Now, the reality is you could probably integrate this, right? It's doable. It's actually not very hard. We could use the integral test for this because the derivative of the denominator is the numerator. So it's actually a very clean integration. So we could, but of course we don't want to go that route if we don't have to do the improper integral. And so the trick here is just basically to look at the leading terms that are in front. And that will tell you what to compare to. All right? Don't worry about the constants. So in other words, I know this is like n over n squared, which is same thing as 1 over n. So I'm going to use the series from n equals 1 to infinity of 1 over n. So that's how I pick it. So that's the biggest question. So how do I know which series to pick for? Again, 9 times out of 10, it's going to be a P series like this. Not always. Well, this is a P series. Remember, you must prove it where P equals 1, So diverges by P series test. I must state this information. So now I know that this series, 1 over n, because yes, there's a harmonic piece that you can also throw out instead of saying P series. You save a few words in your solution, and yes, it will be accepted. So we have here, so in here, a sub n is 2n plus 5 over n squared plus 5n plus 17, where b sub n is 1 over n. Now we're just going to divide. Now the question always goes, well, which one do I divide it by, right? Is it a sub n over b sub n over a sub n? It really doesn't matter because in either scenario, as long as you get a non-zero constant. That's what a question comes up. Well, what about 0? Is that? No, that does not work. So I'm going to take the limit as n approaches infinity of 2n plus 5 over n squared plus 5n plus 17, and I'm going to divide it by 1 over n. Keep change flip if you haven't done fraction division in quite a while, right? This is the same thing as the limit as n approaches infinity of 2n plus 5 over n squared plus 5n plus 17 times, the top just gets times n. You could probably see what the answer is going to be right here, but just in case, the limit as n approaches infinity of 2n squared plus 5n over n squared plus 5n plus 17, which is equal to 2, which is a non-zero constant. So, therefore, the series from n equals 1 to infinity of 2n plus 5 over n squared plus 5n plus 17 converges, diverges, did it to me again, Abner, diverges by the limit comparison test. We remember, that's the big key right here. We had shown that this series diverged, and our series must do the same thing when we get a non-zero. If it doesn't give you a non-zero, I want to say, I should have put up here, and I'll put this at else inconclusive, right? So I forgot about that part. So we'll right here, and we will break. All right, we're gonna get going here. The next one that we have, number 8, is the alternating series test. Now, the alternating series test is basically that we have one of the two scenarios of an alternating series, or that the sequence is itself alternating. So we have either like the sum from -1 to the n of b sub n, or we have the sum from -1 to the n plus 1 of b sub n. And if you notice here, I'm not writing from n equals 1 to infinity. It really doesn't matter if we're starting at 1 or 2 or 3. They're both are going to be the fact that they're alternating. Positive, negative, positive, negative. Remember, they could also look like cosine of pi n. That's the other most common one that can be there. The alternating series comes down to the fact that if the limit as n approaches infinity of the absolute value of a sub n, which would be b sub n, if this is equal to 0 and the absolute value of a sub n is greater than 0, and the absolute value of a sub n is decreasing, all of these, those are like the conditions, then what happens here in my visually what occurs, so I'm actually going to do 3 separate graphs here. This is for the sequence. The first one is the sequence of b sub n, okay? So this would be the absolute value of b sub n going from 1, 2, 3, 4, so 1, 2, 3, 4. And basically what's happening, and onward, that if the conditions hold, then the absolute value, of course, it's positive, but it's decreasing like so, okay? The actual, oh, sorry, that should be A sub n, not B sub n. So therefore, the actual way A sub n looks like would be here, then here, then here, then here, then here. You know, it's going to get closer and closer and closer right there to 0. Okay? Basically, I'm undoing the absolute value, okay? But every single value is less than. Here comes the math magic. So if I look at the series of A sub n, therefore, which is positive and negative, then my first term right here will be A sub 1. Let me actually just change the colors and move it over a little bit. So here's A1. A1, 1, 2, 3, 4, 5. A1 is right there. So, and this is for 1, 2, 3, 4, 5. Now, when I find A2, the distance from A1 to A2, or this is A2, such that when I add these two numbers together, I'm taking a positive number. We're going under a scenario that the first term is positive, plus or minus some value that is less than my first term, because A sub 2, the absolute value of A sub 2 is less than A sub 1. And then the next term is going to be positive, but it's going to be less than A sub 2, so the distance from the point to the new point would be my positive A sub 3. And so every single time you're adding the next term, positive or negative, you're coming a little bit less higher than you were before, a little bit less lower than you were before. And so the terms are going to reach this hypothetical L horizontal asymptote of when you're summing. And again, this is because the alternating series, it's an alternating series where the absolute value of that alternating series is decreasing. So that decreasing aspect needs to be in your conditions of stating it. Okay? So the alternating series test says that you have to state, or first and foremost, that it's an alternating series. Yeah, so that it's positive, negative, positive, negative. You must, that the limit as n approaches infinity of the absolute value of A sub n is equal to 0. I mean, technically, you should be stating that the absolute value of A sub n is greater than 0, but that's kind of like obvious. I'm not really a stickler for that one. And that the absolute value of A sub n is decreasing. If all of these are true, then the series converges by the alternating series test. Yes?
What's the purpose of the third condition?
It's just to prove that you have it's basically stating what the proof shows visually, that these terms are positive and decreasing, which is always an important aspect of it. So it's really kind of, and that's why I said it's because it's an absolute value, by default it is positive. It's just part of that proof behind the scenes that we used that fact that it was positive and going down to visually see that each term is kind of being just a little bit off. Now, if the series of negative 1 to the n of B sub n also, so if the following series, if this converges, but the series from n equals, or the series of b sub n, which is, of course, the absolute value of a sub n, diverges then the series from -1 to n of b sub n, we say that this converges conditionally. One of the most prime examples for this is the series of -1 to the n over n. That's the most common example right there. So this is an alternating series, and it fits all the criteria of the alternating series, and so the alternating series converges, right? But if I took the absolute value of this series, then we get just 1 over n, which is a harmonic series, and we know that that diverges. So therefore, this series right here converges conditionally on the absolute value piece, on the fact of alternating. However, if the series -1 to n of b sub n and the series of b sub n converge, then the series -1 to the n b sub n, which is just stating the fact that it's an alternating series where b sub n is the absolute value, converges absolutely. So I may ask you on the exam to determine if it converges conditionally or if I might say, like, if it does converge, if it's an alternating series, determine if it converges conditionally or absolutely. Now, one other thing about the alternating series that we need to also note is for an alternating series, when looking at a series -1 to the n of b sub n, we know that the absolute value of a sub n plus 1 is always less than the absolute value of a sub n. In other words, each term is progressively closer to the infinite. Well, what happens is you're adding a little bit, subtracting a little bit less, adding even a little bit less, subtracting even more less. So each progressive sum of terms is therefore closer to the infinite sum. So if I want to approximate the series from, n equals 1 to 5, all right, of -1 to the n of b sub n, whatever it is. Or actually, let me give you an actual one there. Over n squared, then this would be -1 over n squared plus -1 over 1 squared plus 1 over 2 squared minus 1 over 3 squared plus 1 over 4 squared minus 1 over 5 squared. And I can add all this up, right, and figure out what this sum is. I can actually calculate by just doing the work. The error of this approximation is just simply the absolute value of a sub 6, the next term, which in this case, the absolute value of that, which is 1 over 36. So I know that my sum is off by no more, and it's basically a Lagrange bound error, that my sum is off by no more than 1 over 36. That next term. And the value of that next term is 1 over 36. That's like the maximum, right? It is the value, because I know I'm going to be going, and I'm going to get closer by 136, which is going to bring me in the other direction to, and yes, you can determine if it's too much or too little, but we're not worried about that fact. That my answer is the next term in the sequence is my error. All right. We're going to fly through. I'm going to get just a little bit long because I just need to, we definitely did start a little bit late, and I think it's important that we get through this next two tests really quickly so that you can practice them tomorrow. Test 9, the root test. Now, I'm going to show you the root test real quick and the ratio test. The root test is just actually it's an extension of the ratio test, but for our purposes in a lecture, I'm not going to really go into the proof too much, but I don't want to prove the root test too much. It's basically you can prove the root test by the ratio test, okay? As I show you this, the last one, which is the ratio test, the granddaddy of all of them, right? A. Basically, if the limit as n approaches infinity of the nth root of the absolute value of a sub n, if this is less than 1, then the series of a sub n converges. Literally, you take the nth root. So the premise behind here is that you're thinking about the growth rate of the nth root of the actual function. And as long as if that's something that's going to be less than 1, and exactly 0 is also less than 1, right? Then the series itself is going to converge. You're literally, all you need to do is add the nth root of this. And again, it's one of those obvious ones where you have something that's everything to the nth power. All right, so you have blah, 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 blah to the nth power. And you're like, oh, how do I do that? Well, if you take the nth root, then the nth power and nth root will cancel each other out. And then you can test it, whatever's left over. Now, does that do as a limit? B. If the limit as n goes to infinity of the, once again, nth root of the absolute value of a sub n, if this is greater than 1, then that means our series diverges. If by even taking the nth root of the growth, of the sum of the sequence that we're taking, if that is even greater than the ratio of 1, then that means it's growing too fast for us. And therefore, it's going to always diverge. Again, and I know I'm doing a little bit backwards, but for time scenarios, once you see the root test, if you haven't done the ratio test, you can prove it that way. You can apply the ratio test to the root test to prove it. And C, if the limit as n approaches infinity of the nth root of the absolute value of a sub n equals the 1, then inconclusive. Doesn't help us. All right. Again, I'm trying to go through these last ones really quickly. I'm just not going to give us an example of the next one. I just want to put down in it. In workshop, I think one of the major things for workshop tomorrow will be that ratio test. So, the ratio test, which is our final test. And a lot of people will see that you can use the ratio test in most all the other scenarios as a placeholder for the integral test, as a placeholder for direct compare, all those different ones. Oftentimes you can just use the ratio test if it works out for you. The math does work out. The math becomes a little bit more technical though, versus, oh, that's a p-series, done, right? So that's the big difference. So you want to do this if your series though of a sub n has some, series that's like x to the n, which does have a special name for it, but basically we have something the proof behind it is that we're going to treat this like a geometric series, all right? If this series is geometric, and this will lead a lot to we have in our next lecture, then we know that the series of x to the n converges when what? When the absolute value of x is less than 1, right? And therefore, if the limit as n approaches infinity of the absolute value of x sub n plus 1 over x sub n, which is the common ratio, we call that the common ratio. You take the net. How do you calculate the common ratio in a geometric sequence? you take the next term, and well, you divide the two terms. Did I get it backwards here? No, right? Yeah. You want the terms, yeah. So you want, because you want to be less than 1. So if this is less than 1, then the series converges. And so the reason behind a division there is that's how you calculate the common ratio. Okay? So therefore, and I'll finish off this part right here, the ratio test states the following 3 things, which is basically what we just did with the root test. A, if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is less than 1, then the series of a sub n converges, as we just show. And again, this is a by ratio test. The math here is a little bit trickier to do. You have to see that practice tomorrow. If the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, if this is greater than 1, then the series of a sub n diverges, once again by ratio test. And C, if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, if this is equal to 1, then inconclusive. And that's kind of really the issue with the ratio test, is that in a lot of scenarios you do get something that's inconclusive, and therefore you are forced to use one of those other tests. So you literally, wherever you see an n, you replace every n with n plus 1. And you divide it by the original series. Or keep, change, flip. It's a lot easier. You multiply by the reciprocal. The math is a lot easier when you plug in n plus 1 and then you multiply by the reciprocal of the given series, which is the same thing as dividing by that given series. Thank you. Sorry for going a little bit over today. There's some good examples of this. You'll have your pickings of them tomorrow. Do a ratio test problem with it.